Well, first of all, thank you for inviting me to come over and give this talk. It's always nice to visit Israel and see some old colleagues. I was asked to give a talk in introductory letter that you wrote to me, and you say, oh, give a talk on quantum channels. I say, well, why quantum channels? It's not necessarily my area of expertise, but then I thought, why not, right? So you've asked, and your ticket will be paid. You go to Israel, so I may as well talk about quantum channels. So I'm going to give those 3 lectures on quantum channels, and I will use the whiteboard for 2 reasons. One is, of course, it's just kind of a more human interface, and I don't have to go and race. I can go at a slower pace. So essentially, you know, when you come to a school like this and you don't know the audience, it's quite a challenge because you have to think about the entry point, right? Where do I start the whole narrative? So I would like to know how many of you knows about density operators? Well, a lot. Okay. So how many of you would identify yourself as computer scientists? Well, that's a tiny minority in this audience. And how many of you would identify yourself as hardcore physicists? Okay, if I drop this adjective hardcore, how many of you would identify yourself as physicists? Okay, pretty much. And how many of you would claim that you are a mathematician, really? Lucky you. Okay, fine. So that gives me some idea. So So in this case, if density operators are known to you, let me just start by saying, obviously, you know, when you learn quantum physics, sooner or later, you talk about how you describe a system, and then you assign a state vector to this system, and then you have a unitary evolution of this system, and later you learn about quantum entanglement. And the way it is defined is that you have 2 subsystems, right? And you have a state of 2 subsystems that is not separable in a way that you cannot assign the state vector to a subsystem. So that's almost a definition of a quantum entanglement. Then, of course, the first question you ask yourself, okay, then how do I describe a subsystem? And then you introduce density operators that you can assign to any subsystems, even if that subsystem is entangled with anything else. So now the question is, of course, okay, now you have density operator, and we know that when we deal with state vectors and systems, and those systems are isolated, there's just like one unitary evolution, and that's it. So how about the most general evolution of a density operator? So is it unitary? Is it obviously, it may be more complicated than unitary. So essentially my first lecture will be about this, and I'll try to provide you actually maybe 3 approaches to quantum channels. That is the most general class of evolution of density operators that we can describe in a sensible way. And that would be like top-down approach. So I start from the big unitary evolution of the whole, whatever the isolated system is. You keep extending the system until you end up with something that you claim is isolated. It could be the whole universe, but that's one approach. And then, you know, you just look at the embedded system and say, okay, the whole thing evolves in a unitary way. I'm going to draw this potato. This is actually my isolated system, and embedded there is a subsystem, right? And we know that the whole thing evolves according to some unitary evolution U, but this embedded potato, right, changes there under the influence of this unitary evolution. And then the reasonable question to ask is, okay, is there a compact way to describe the evolution of this subsystem to this system? So we are interested in this particular map that is induced by the unitary, but perhaps this one can be also somehow written nicely without necessarily referring to the evolution of the universe, right? And so the question is first, is there such a map that can be described in a nice, succinct way? And if there is, what is it? So the answer to the first question is, in general, there isn't. So in general, we cannot do it. However, there's always however, because there wouldn't be a lecture without this however. However, if this subsystem initially is not entangled or correlated with everything that it's going to interact in the process of going from here to there, there is. So there is assumption, tiny assumption. It's related to a few things that I will talk later on. But under this assumption, and this is a spoiler, so there is a map. So if this thing here is described by the density operator rho, so then this density operator rho evolves into something that can always be written as a sum of I, and let me just write it as E sub I rho EI dagger, where, so this is the density operator that you associate with your initial subsystem, and it evolves into another density operator, rho prime, say, that can be written as a sum. There's the operator sum, and I have operator E sub I rho, E sub I dagger here. And the only thing I require here, as you will see in a moment, is that the sum of, this is the so-called normalization condition. So just to make sure that I get the density operator that has trace 1, we'll come to this in a moment. So we require that the sum of the product, EI dagger EI, is equal to the identity. So that's the spoiler. And now the purpose of the first lecture is to show you that, so it's kind of to derive this form, which is known, there will be some name dropping. You know, usually things are very simple, but when you start adding names and you hear the topic for the first time, you're kind of intimidated by those names. So I'll tell you about all the names that I use, but don't be intimidated by the names. So those are known as Krauss operators, okay? And this thing is known as a Krauss form. So there was a guy called Krauss who obviously thought about it, and they are known as Krauss operators. So I'm going to show you that this kind of global picture, big picture, implies this particular form. And then we will look later, so this is a top-down approach, going from the whole to the subsystem. In my second lecture, I'll try to take bottom-up approach. So I'll just look at the Krauss form and we'll tell you something. I'll try to sort of take more constructive approach and show how you can compose any interesting operator, a class of operations on a density operator starting from this condition. And in between, I'm going to pay a tribute to our only mathematician in the audience, and I'm going to sort of show you how a mathematician may approach this problem. And you know, mathematicians usually just, well, they have this privilege, right? So not to ask questions about the meaning of things, but mostly about the form of the things. So they say, well, I don't care about the underlying physics, but suppose I just define the class of maps as any map that preserves the property of the density operator. So a mathematician may say, the class of really reasonable map to consider would be a class of maps that preserve the positivity of the density operator. So if you know about the density operator, mathematically speaking, they are defined by the two properties. They are positive semi-definite, and the trace of the density operator is equal to 1. So a mathematician may say, any map that preserves this property is a good, valid, kosher, is kosher a good word? Proper map, right, that you can have. And therefore, you may say any map that is positive, that means preserves positivity, and trace preserving will be of this form. This is not true. And this is actually an interesting thing. It's a good thing to remember that sometimes, you know, the the power of mathematical abstraction is huge, and it's, you're encouraged to explore it to the limits. But sometimes there's a drop of this physical intuition that is needed to see that sometimes you can go grossly wrong if you walk in the wrong direction. So you will see that the maps of this type are not positive, preserving positivity, trace preserving map, but we add one extra word. They be called completely positive trace preserving maps. And I will tell you about this. So this is a preamble. At least you know where we are going. So let's start with deriving this form first, right? And for this, we have two systems here. So we have the system we care about, call it the system, and we have whatever surrounds this system. So let me just assume for simplicity that, this thing will interact with the environment. We can add other subsystems, but that's not necessary. So the scene, the backdrop, mathematical backdrop for this narrative is a Hilbert space pertaining to the system, tensor product with a Hilbert space pertaining to the environment. And let me just pick up a basis in the environment, an orthonormal basis. I call it E sub I, and it's an orthonormal basis. So here's a mathematical backdrop for our narrative, right? The Hilbert space, which is a tensor product. I'm picking up this orthonormal basis in the environment. And so if I just do this big unitary evolution, no matter what it is, can be written in the form where I write this as U sum over ij, E, ij, tensor product, EI, EJ. So it should be obvious that you can always do it, right? So what I did here, there's not that much of the mathematical magic here. This outer product is just a convenient basis to write any operator in the environment space. So it's EI here, EJ here. And then I can, of course, also pick up sort of a good basis for the operator. So by the way, I understand that you understand this notation, right? So it's like a big matrix where the only entry is in ij entry. So this ith row and j column somewhere. So that's number one, and everything else is zero. So it's a very common basis that you can always pick up if you want to write any matrix whatsoever. So this can always be written this way. And this thing is an operator, is a matrix, which acts on this space, right? On the system space. So everything that can be just combined into this operator. Of course, now those operators, E, I, J, are not just any operators. This is a unitary matrix. You know that in finite dimensional spaces, we just require that U dagger is equal to U dagger, U, and is equal to the identity. So clearly, there are some restrictions imposed on those operators, E, I, J. But let me just first, before we come to those restrictions, let's see what it implies for the evolution of the system and the environment. So let me also take this assumption first. We'll drop this assumption in a moment that this state is initially in a pure state, right? So before it starts interacting with the environment, you can describe it, if you want, by a state vector. You don't have to go to the density operator formulas. So in which case, under this operator U, if you have a state psi of your system and some state E of the environment, this will evolve under this unitary operator, and then let me just put this operator here, E, I, J, E, I, and J. That will act on psi. and then tensor product, and this outer product here, EI, EJ, will act on E. If at any point anything is not clear, shout, please. I'll better slow down and say less than just mislead you and say too many things. So so now it's just a question of, this basis here, this orthonormal basis, we can choose anyway, really. Any orthonormal basis will do. And now when you look at this expression, you can see it's always convenient to pick it up in such a way that maybe the initial state of the environment it will be just one element of this basis, because then you can just drop few terms here. So these terms will just have only one element, and the rest will be 0. So let's assume that you pick up your EI in such a way that sort of one of them, say E1, coincides with E, in which case you can write the whole thing as, so you see then this sum, really, that you don't have to sum over two different indices in this case. The J will be truncated into, or will be fixed into one value, say E1. So essentially then you have a sum over one element. So you can write this as a sum, sorry, over one index. So sum over I, EI, because J is fixed then, acting on psi, tensor. I'll drop the tensor product from now on. Tensor product sign, I mean. Yeah. So this is how it looks like. So the system initially in some pure state psi and the environment in some state E evolve under this unitary operator in such a way that the system is modified by this operator EI, and the environment there's a relative state of the environment corresponding to this modification. So there's effect on psi described by E sub I and the corresponding state of the environment EI. And then we have a sum of those things. So far, so good, right? Now, let's go back to the, let's say something now about those Krauss operators. Yes, please.
What is the ij line equal to the, like, where did the J go?
Sorry, the J?
Yeah, the EJ and the E to J and the I.
Right, so what I'm saying here, at this point here, I can choose the basis that is convenient for me. And I'm going to choose so that E is the element of the basis. So that the initial state, say, is equal to E1, for example. So that means that, by choosing this basis, that means that, so let E is going to be equal to E1, right? So at this point here, I have J becomes 1, and every other element is equal to 0 because it's an orthonormal basis. So essentially, I will have something like sum over I, and J index will be fixed to 1, which you just could be fixed to anything, to 42 if you want, or choose your favorite number, right? So it doesn't really matter, so let's ignore it. So we only have one index to sum over, and it's EI, okay? Yes? Correct, yes. Any unitary operator. We are dealing with huge, but potentially huge, but finite dimensional Hilbert spaces. So it's just writing this matrix in a tensor product. So, this matrix is acting on a tensor product structure. So it has a block block form. So you can always write it in this way. In fact, if you have sort of more, if you think more in terms of if you have more visual thinking, I don't want to confuse you too much, but if you think about this matrix U, quite often, if you just reverse if you reverse the system with the environment, if you just write it in a different order, so this matrix will be a huge matrix, but it will be it will be a block matrix, and those operators can be written as E11, E12, and so on and so forth. But to have this picture, just be careful. Not the way I wrote it here. You have to flip the orders in order to have this particular image. But if it helps you, that...
Yeah, but here you didn't demand this you be unitary. Here you can be also not unitary.
Well, I assume it is unitary, and it has some consequences, but I haven't discussed those consequences yet, okay? So if you just, obviously, if it is unitary, if you impose this unitarity condition, then those operators are not just any operators. They have to conform to this unitarity condition for the whole matrix. But there's just only one condition. So you see, just going back to your question here, so this, from all those elements, using this kind of picture here, we are just picking up one column, because we fix the state of the environment. It will be one of them here. And we simply just pick up one column, so you'll have something like, here it will be like E12, E22, E32, and so on and so forth. So one index is just fixed, and it's superfluous. So therefore, you don't include it in the analysis. Okay, so the only condition that really matters, there are a few conditions there, but the only one that we really use is associated with the fact that if you have this unitary evolution, then obviously this vector has to, the unitary evolutions preserve the length of the vector. So if this is of length 1 that is properly normalized, the whole thing here has to be properly normalized, right? So if you write the normalization condition, so on this side, it will be just psi, E, E. And on the other side, it will be sum over I and j. And I will have psi, EI dagger, EJ, psi. And I will have here EI, EJ. Yes? We are. And that will pose a bit of a problem for my composition here, because I will provide you with extra information if I start writing at the top, but I will have to erase some information as well. So if you're okay with that, I'm happy to do that. Let me just... Right, so can you at least see the bottom line here? No, maybe. Okay. The ground state. So let me just, I will rewrite it. Which part I should, okay, so let me just erase this part. And let me just say that, okay, so if you look at this condition here, so this, of course, is equal to 1. And this part here is equal to Kroneker's delta. So the condition really says that, so it goes back to the statement that sum over I, because the Kroneker's delta kills one index here, right? Sum over I, psi, EI dagger, EI psi is equal to 1. But for this to happen, then you have to have this term, the sum of all those terms here equal to the identity. So the condition, so we're coming to this condition. So we derived from the big unitary evolution this condition. We sort of mentally associate, when you see this condition, you think about this condition being responsible for making sure that the probabilities are preserved. So the normalization is preserved. It comes from the fact, it can be derived by imposing this, looking at the unitary operator and using the defining property of the unitary operator, but it can also be derived by imposing the normalization on both sides. And in this case, it just simply says, when you look at it this way, it simply says that the norm of the vector on both sides is the same. And when we switch into the density operator language, this condition here will be responsible for preserving the trace of the density operator, which is the same thing, making sure that the probabilities on both sides add up to 1, right? Any questions at this point? Okay, so we are learning slowly something, right, about the. So I'll try to restrict myself to the top of the whiteboard. So we already have one property of those Krauss operator. So remember that our evolution is of this form: sum over I, EI, psi, EI here. And we know that we already derived one property of the Krauss operators. Now, of course, you may also want to say, okay, you derived this in a very special case because there's a pure state there. There's a pure state of the environment. Well, first of all, the pure state of the environment is not such a big issue, right? So you can always, if it is in a mixed state, you can always extend it to some system. You can purify it to the system that is pure. So that's not a big deal. And the fact here that this is a pure system is also not a big deal, as I'll show to you in a moment. So first of all, let's phrase this evolution here, even though we have state vectors on both sides, but let's phrase it in terms of density operators, right? So we can, and you know that for a state vector, we have a density operator that is a projector on that state vector. So on the left-hand side, we'll have a projector on psi, tensor projector on some fixed state of the environment, and that evolves into sum over I and j. And here I'll have E, I, psi, projector on psi, EJ dagger. And here I have EI and EJ. So it's a tensor here. So not a big deal, right? A very simple algebra. I just switch from the state vectors. I have pure states, so I have state vectors, but I just wrote the same evolution in terms of density operators. But then what I can do is to say, okay, now I'm not interested in the environment. I don't control the environment. I have no idea what's going on in this environment. Can I just simply forget about it? And you know that a mathematical way of saying forget about it, don't pay attention to this, is equal to tracing over it in terms of density operator. So what I'm going to do, I'm going to take a partial trace at this point. I'm just going to forget about the environment. So one thing about the one property of trace that I'm going to be using is, that you may know or not know, is if I have a trace of this outer product A, B, that's equal to B to the inner product BA. So the trace turns outer products into inner products. If you don't know this, you can derive it as a simple exercise. So, okay, I'm just taking a partial trace. I'm just over the environment. I'm just dropping the environment. So that means I have to trace over this part and over this part. So this survives because it's a partial trace only. So psi, projector on psi, evolves to, now the trace of this is following this formula is equal to EJ, EI, and that is a Kroneker's delta IJ, right? So again, it kills one index, so therefore this expression here becomes now sum over EI, psi, EI dagger. So we have just one index here. So we derived almost this expression here, except that this is for the pure state. But it already looks fine, right? Almost there. So now the final thing is to notice that if we can have this evolution for a pure state, and it's a linear thing, right? And any density operator can be always represented as a mixture of pure states. The simplest decomposition is, of course, to use eigenvalues and eigenvectors of the density operator, but you don't have to. So any density operator can always be written as a mixture, and if in doubt, go for the spectral decomposition. That's the simplest one. So once we have this, so that you can, if this is true for any psi, and this is true for any psi, therefore it has to be true for a convex sum of projectors on psi. So that means it's true for this kind of, for any density operator, because any density operator can be decomposed into a sum of projectors. So we are done. But of course, you know, now we say, okay, we managed to go from the top to this form. We derived the Krauss form from a big unitary evolution of the whole system. Now, what else can we just say about those operators? You know, the natural thing, once you have the result, you are not stopping there. You're asking questions like, you're curious, like, so you're asking questions like, okay, how many operators do you really need? Is there a unique set of operators? Given a unitary operator, you know, do we have just one set or many sets? So there are obviously questions to be asked, and they have physical interpretation. So, one question that we can resolve right away, looking at this form here, is there only one set of Krauss operator corresponding to this evolution? So can we describe the same map, the same transformation of density operator using a different set of Krauss operators? And if so, how are they related to each other? If you look at this expression here, you know, we made this assumption, we just pick up an orthonormal basis in the environment. And the only thing we cared, as we discussed here, was that, well, you know, it's convenient to choose at least one vector from the basis to be the initial state of the environment. But otherwise, we have a freedom to choose the basis as, you know, as we wish, essentially. There's nothing compelling there. Yes, please.
It's taking you a big back, but can we relax the assumption that they are in a product states, system in the environment? The environment may be mixed, but maybe mixed because it's in some huge non-product state with the environment. Is there a generalization of this kind?
Well, okay. So here we have this simplified version. We have pure states of the system and the environment. So obviously, they are separable here. But to answer your question, what we can do, I mean, this Krauss form can be derived with this assumption that you can, you know, the environment can be in the mixed state, but assuming that it is in a pure state is not a big deal, because you can simply extend this environment and think about a new environment, and eventually, by purification argument, you can go to a pure state. So if you include everything, that's fine. So the assumption that the environment is in a pure state is not a big deal. Now, what about the system? So the system can be in a mixed state. Now, you can consider the following situation. So here is your system. Let me just draw environment here, and let me just draw another system here. So we have like 3 systems right now. So this thing, the system, can initially be entangled with something else. And so therefore, it could be in the mixed state. But then, we assume that this state doesn't play the role in the interaction. It's not part of this unitary evolution. So that unitary evolution happens here. That system is simply just like a passive observer in this case. So then it works. So I'm just simplifying this analysis a little bit. I will assume that this system is in a mixed state originally, but has no correlation whatsoever initially with the environment. So the way to think about it is the system should not be correlated with whatever is going to interact in this process.
So this we cannot relax.
This we cannot, unfortunately. No. Yeah. This is, yeah. So there is, of course, if I had like a few more lectures to give, I would go into analyzing something that is called Markov approximation when this kind of assumption is justified. There's lots of like, blah, 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 blah. You can talk about it for a few lectures. Physicists usually assume that then, because, this thing will be an issue when you want to compose channels. So you have the system and the environment gets entangled at the end of the operation, right? And then we want to have another channel. And you say, hey, wait a minute, but the initial condition is not satisfied. How you can compose the channel? So the composition of the channels will be only possible under this so-called Markov approximation. The system is such that it's sort of like, decouples itself from the environment, or maybe this kind of environment entanglement is not essential. So the idea is every single time you have to somehow add a different type of environment. Maybe I'll talk a little bit about it later. So if I can defer your question maybe to the last lecture, then I'll say a few words about it.
I want to follow up question on this. How do I verify that this is the initial state?
So you can verify if you have a system, right, in your lab. So that's, if I understood your question correctly, I come to the lab and I want to just analyze the system in terms of a channel, and I don't know whether my system is entangled with it's going to interact or not. So well, most likely it may be entangled grossly with something else that is not going to be part of this interaction, this unitary operation. So this is the system you care about, this one, and it may be entangled with all kind of stuff in your lab, which is always the case, right? And now, but your experiment will be. Control experiment will involve only interactions between those parts. So if this is the case, it's okay. The problem is if this is already entangled with this thing here. And of course, the only thing you can do is to maybe do a state tomography on this and see that this is a mixed state. If it is a mixed state, it's entangled with something, but you're not sure whether this is the case or this is the case. So you have to make your judgment in this particular case. But looking at the system alone and just seeing that this is in a mixed state tells you it's entangled with something because it's not in a pure state. But unfortunately, you have to use some extra information to judge whether your channel sort of initial condition is satisfied or not. Usually, you don't know. So that's, we went already into a few subtle points at the very beginning, but let me see, what did I try? Oh yeah, I tried to tell you that, before you asked this good question, I tried to tell you that there is not a unique choice of those Krauss operators, because suppose I choose another basis, suppose I choose basis f, j, which is also orthonormal, so I can insert here the projector, or I can do the decomposition of identity here. So let me just put fj, the fj. So in other words, if I can write this expression here as sum over ij, ei, acting on psi, and I have here fj, ei. This is equal to the identity. I'm just using the sum over j. I'm using the fact that the basis is complete, right? And so hence this thing can be written as sum over j. And let me write this part here, sum over I, fj ei, and here I have fj. So you see, it's a beauty, of course, of the Dirac notation that you can just write first this kind of thing, say, oh, this is identity. I use the composition of the identity in any basis. Then I just gently attach this into this operator and I say, ah, yeah, this is actually a number. And I take all those numbers here. And then you look at this and you say, oh, but this is, of course, this corresponds to a matrix that describes the change of the basis. You go from one orthonormal basis, which is EI, to another orthonormal basis, which is FJ. So this is a unitary matrix here. I hope I will not confuse you too much. Let me just use U, but this is not the same U that you saw before. So this is a sum over I. So let this be called U. UJI, but be careful, it's not the big unitary thing, it's a different unitary operator. EI, tensor FJ. So call this new operator, oh, sorry, I'm just the bottom line, I know, but this is FJ, yeah. Yes, please. You're absolutely right, yes, thank you. The psi should be here. Sorry? So, guys, what do you want me just to write on the top, to stay on this side of the whiteboard? Do you want me to dance or just, there are limits added to things I can perform in front of you, and you want to, maybe you guys come and lift this whiteboard a little bit as I write on them. So that would be a good challenge for you, a little bit of exercise in the morning, But what I'm saying here is that, yeah, and you're right. So this psi, thank you, that psi also comes here. So as you can see that what this expression says, the second property of those operators is that they are not unique. There's a unitary freedom. So what time should I finish?
You had many questions. You can go 5 more minutes.
5 more minutes, okay. I'm almost done, actually. I just wanted to give you some examples, but maybe I give you examples as a simple exercise for a coffee break. So so what did we learn, all right, so far? So we learned that any subsystem, given this initial condition that we discussed a little bit, that is not correlated with whatever it's going to interact with, evolution of density operator of such a system can always be written in the Krauss form, where we have those Krauss operators. Then the next question is, what kind of properties those operators satisfy? We say, well, the only non-trivial property is this one. You're free to choose pretty much anything as long as they satisfy this property. And you can argue about this property in 2 ways. You can say, well, it has to be the case because those are like sub-matrices in this big unitary operator that transforms the whole system. Therefore, they have to conform to the unitarity condition of the whole thing. You can also just derive it by saying, oh, well, they are responsible for normalization, so we use this fact just to derive this condition. Then the second thing we learn about the Krauss operator, that there's not just only one set for a given transformation. So for a given map, there's not just like one set of the Krauss operator. In fact, we have a unitary choice of choosing. So if you write those operators, so for example, let me just give you an example. Consider the following channel. Take a qubit density operator that is mapped into something that is half identity plus half Z operator. By Z, I mean Pauli Z operator, sigma Z. And let me just write, I'm sorry, but I will have to write at the bottom. You can come and have a look at it later. So that evolves into something that is a projector on 0 plus projector on 1. So I gave you as an example 2 simple channels here. And you can see that they are written in the Krauss form. And then, yeah, I don't know what to do with this. I would like you to see it. So the first one, your interpretation of this channel is, with probability half, nothing happens here. And with probability half, you apply Z operator to your system, which we write as identity being 2 Krauss operator. More precisely, 1 over square root of 2 identity is the Krauss operator. And here, 1 over square root of 2 Z is the Krauss operator. So we have 2 Krauss operators here. Let me write them this way, just to show you something. So this is 1 over square root of 2 identity and 1 over square root of 2 Z operator. Now, here, I have another channel, which is, you have 2 projectors here. The first Krauss operator is projector on 0. And the second Krauss operator is the projector on 1. And you may have a different interpretation of this. I mean, the interpretation of this channel is, okay, it looks like you are projecting the density operator on 0, and you're also projecting it on 1. So it's like you are performing a measurement here in the computational basis, 0 or 1, trying to figure out whether your system is in 0 and 1. But you are adding those things together, so it looks like you performed a measurement, but you forgot what it was, or you just simply didn't look at the dial, and therefore there's still this uncertainty involved. We'll come to this interpretation later, but what I want you to see, and this is leaving you as some kind of example, is that if you think about those 2 Krauss operators for the first channel as a vector, where you just plug the operators as the entries, and take the unitary matrix, 1, 1, 1, minus 1. So here, and I have to erase this part. Minus is missing, thank you. I really appreciate that you just look carefully and correct my mistake. So that means at least I'm not losing the audience. So this is really so reassuring. So I want you to show that under this unitary transformation, you will discover that, in fact, the 2 channels are the same, because the Krauss operator are related by this unitary transformation here. Even though the interpretation I gave you is different, nonetheless, it's just they describe the same transformation of the density operator. So in summary, just for this lecture, the summary goes in few points. First, top-down approach. From the big unitary, I derived the dynamics of the density operator in the Krauss form. Those Krauss operators, in order just to make sure that the probabilities are properly satisfied, have to satisfy this condition that I conveniently erased now, that the sum of EI dagger EI is equal to the identity. Moreover, we also learned that the Krauss operators are not unique for a given map. So you have this unitary freedom, and you now understand that this unitary freedom is also associated with choosing a different basis in the environment, in the secondary system. And I think that the next lecture will just look more closely at the Krauss form, and we'll try to understand a little bit better what it means in terms of other operations like adding a system or forgetting about the system. Can we phrase partial trace? Can we phrase some operations like adding a subsystem in the Krauss form. So if we can, that the Krauss form will become a beautiful tool that you can use to describe subdynamics. So that's, unless I'm done. So if,
We have time for questions.
yes, please.
Going back maybe to the entanglement question, could I imagine there was time in the past where the system were not entangled and they formed another unitary operator that entangled them, and then look at the time evolution of the product of the UU with respect to four and the frequencies that they often equal, and try to find a channel for that. So like not limiting myself to a starting point where the systems are not entangled.
I'm not sure I got all aspects of your questions. Are you saying that, is it related maybe to the previous question I had, that when you are dealing with a situation, you never know whether this system is entangled with something or not? So maybe this let me just draw a diagram. If this doesn't clarify the situation, I'm happy to answer this question later on talking to you. But so what we are saying is this. In terms of this unitary evolution, I have the system and I have the environment that I bring, okay? So this is your system that can be entangled with something, and that something doesn't participate in the evolution. You know, those two things could have interacted in the past. We don't care about that. So that's fine. But this environment, we assume, is just simply decoupled from the system. So now the two interact. The environment gets entangled now with the system. And then we want to go, so the system is now in some state rho prime. It's entangled with this environment here. And then we want to go through another channel. And then that's a problem here. Simply, we cannot just plug in those two and continue because the condition of separability is not satisfied. What you do in this case, you just simply throw this environment, just bring another environment and continue. So that's the way it's, only in this way, when these conditions are satisfied, then you just can apply this formally, this Krauss form. In practice, of course, you may say, well, you know, it may be that the system interacted and then this entanglement is very weak. You know, you can do this, but in order to do this, there's lots of yada yada here. So, you know, there are some, like you talk about Markov approximation, you talk about a few things. It's possible, but again, essentially, you have to just say that this yada yada corresponds to essentially, okay, just neglecting the entanglement with this part. Actually, you know, I didn't anticipate that we'll go into the most subtle part of this quantum channel on the lecture number 1. So I thought that I'll just mention this at the very end, but you forced me into answering those questions.
Okay, so yes, I have a question. So maybe you could explain to us how you modulate innovation payloads. Suppose that one guy is in qubits, part of them are reached with their destination, and the other parts are just get lost. So could you learn that by Carry separators? There is a way to do that.
To describe errors, you mean?
Deletion errors, not errors, but deletion of qubits.
Deletion of qubit. Yes, you can. You can, and then actually the next lecture will be about how to describe at least one aspect of what you are saying. There are two things that are usually we don't capture quite in this picture exactly. They involve bringing one system in or also dropping the system or just deleting it. Those can be described by Krauss operators. Of course, you may say they can also be described by a big unitary operator, but involving some other degrees of freedom, right? If you bring systems, you involve the spatial degrees of freedom, but we usually don't care about those degrees of freedoms here. So there is a shortcut, a convenient mathematical shortcut, a Krauss operator, that would just correspond to bringing the system in, but also there is you can express partial trace, or trace for that matter, as a Krauss operator. You can think about it because you can figure this out yourself, but I will tell you what it is. I guess I'm talking later today, right? Right, right. So you know, by this afternoon you will know how to do it. Please.
So to take the two channels in the bottom left.
Yes.
And the two cross operators for the equivalent of the unitary.
Yes.
But they will act very differently even in the zero state. So the first one will keep me in the pure state, and the second one will actually change my, I will be even not in any real state. I mean, I will be half zero.
Well, think about it. So it's a very good question. It's a conceptual question which can be related to the following one. Suppose, think about the whole thing here, that this channel is me providing you states, right? All it means that if you think about, you can think about the pure states. So in the first case, I have a pure state. My initial density operator is a pure state. And I give to you either, I toss a coin, right? Probability half, I give you this pure state, suppose state 0, just say, let's make it even simpler, state 0. But with probability half, I apply a unitary operator to this state and give it to you. So this is Z operator, that could be X, it doesn't matter. So you have two different pure states, but you don't know which one it is, because I don't tell you. So the best you can do is to associate density operator. You say with probability half is this state, and with probability half is the other state. So that's scenario number one. What I'm saying here is equivalent to the different scenario, where I have a pure state, and this operator projects, you know, on something and creates a different pure state, state 0. So that corresponds to giving you state 0 or giving you state 1. So it's a different sort of a mixture, but this different mixture corresponds to the same density operator. So you see that density, if you have a density operator, there are many possible preparations that lead to the same density operator. So density operator doesn't tell you quite exactly how the state was prepared. So if you take maximally mixed, for example, state of a qubit, it could be prepared by tossing a coin and giving you state 0 and state 1 with equal probability. It could be tossing a coin and giving you state 0 plus 1 with probability half and 0 minus 1 with probability half. It could be even prepared by creating maximally entangled state of two qubits and giving you one of them. So they all describe, what you get is described by this density operator, which is maximally mixed, even though the three preparations are completely different. So this is actually the channel equivalent on this. The channel will generate a mixture of this type or mixture of this type. And even those, if you look at the components of the mixture, they are different, but the density operator will be the same unless you gain some knowledge about the preparation, in which case you then change the density operator. Because you know the density operator has this property that partially it represents the quantum aspects of being uncertain, but partially the lack of your knowledge about the preparation of the state. So the two are combined in the density operator here. Did I answer your question? But you know,
From this to the coffee, right? And thank the speaker again.
sure.